Hello everyone, welcome to topic 6.8, enthalpy of formation. By the end of this, you should be able to calculate the enthalpy change for a chemical or physical process based on the standard enthalpies of formation. We will be working with this equation, which was introduced in previous section, and we're going to continue to refine it. So, in order for a chemical reaction to occur, bonds need to be broken and bonds need to be formed. Please remember again that bond breaking is an endothermic process where delta H is positive and energy is being transferred from the surroundings into the system. Bond forming is an exothermic process where delta H is negative and energy is being transferred from the system to the surroundings. Standard enthalpy is abbreviated as delta H with this standard little degree sign. This symbol here tells us that we are dealing with a standard state, which is 1 mole. So the standard state, like what standard conditions are for this reference point, is 1 mole, 1 atmosphere, so pressure is 1 atmosphere, and is 298 Kelvin or 25 degrees Celsius, which is about room temperature. In 6.7, you learned how to use the bond energies to calculate the enthalpy for a reaction. In this section, we're going to look at the enthalpy for a reaction by looking at the energy of the molecule as a whole entity. So the enthalpy of formation at standard state, or delta H, standard notation F, is the energy that occurs with the formation of 1 mole of a substance, and this is usually from its elemental components. Okay. So it's key to remember that. So any substance that exists as its element, its standard enthalpy of formation. So like silver solid. Oops, not gas. Thinking of my next one. So silver solid, it has a delta H of formation equal to 0. Hydrogen gas, because that is how it exists as an element, that is its like standard elemental state, its enthalpy of formation is also 0. So when we look at a compound's enthalpy of formation, it is from its elemental components, because that is how they exist in their most like rudimentary or like smallest, most simplest form in nature. Okay, so the enthalpy of reaction at standard state, or delta H of reaction, is the interchange that occurs for a reaction. The different subscripts like RXN or F indicate the type of enthalpy you're working with, so pay attention. Anytime you see the standard notation, you need to make sure you are working with elements in their standard state. Okay. This is similar to what we looked at in in the previous section when we talked about bond enthalpies, but remember, bond enthalpy ended up being reactants minus products. Here it's different. You're looking at your final energy state minus your initial energy state, so it's more of a change. Whereas in bond enthalpy, you're looking at bonds broken minus bonds formed. Okay. So we can see that the enthalpy of a reaction is equal to the sum of the formations of the enthalpies of products minus the sum of the formation of enthalpies of the reactants. You also need to make sure you're accounting for moles in it, and that's usually multiplied to the enthalpy of formation for each substance. So you multiply it through. And we'll look at an example. Most textbooks have a table of thermodynamic data. It's in the appendix, definitely in R, so you'll want to flip back. You can also, and this whole note set is posted as Schoology, so you can pull these up, and these are all live links, and I know that this one, the webassign.net Tro Chemistry, one does work and it is live, so you can use that one. This is also one for bond energies in case you need it. Okay, so let's look at how we can apply these. So is the combustion of propane endothermic or exothermic? How much energy is absorbed or released? Assume standard conditions. Okay, so we first need to look at the balanced reaction for the combustion of propane. So the equation for propane is C3H8, and that is a gas. It's important to figure that one out. Plus oxygen gas, because it's combustion, so it's always going to burn in the presence of oxygen. And any combustion always yields carbon dioxide gas and water gas. Okay, so now we need to balance the equation. Please pause the video at this point and balance this reaction. Okay, checking in, you should have gotten 5, 3, and 4 for your balanced reaction. Now we're going to use the equation from previous, so this one up here, and we are going to determine the delta H for this reaction at standard conditions. Okay, so we're going to do our products first. So it is the sum of the products, so I have 3 carbon dioxide, so I need to look up the enthalpy of formation for carbon dioxide in my table. So you would click on this link or use your textbook, and you should see that it is negative 393.5 kilojoules per mole. And we're going to add, because it's the sum, that is what this means, add all the products together. And then we have 4 waters, and you would look up water, which is water gas, which is negative 241.8 kilojoules per mole. And yes, there are different values depending on the state of matter. So you do need to make sure you are paying attention to which state of matter. I do know that this one is a gas because it is a combustion reaction, and that is typically at higher temperatures. So water would be in the steam or vapor state. So we would be using it as a gas. So we've run out of our products, so now we're going to subtract our reactants. So we have 1 propane, and we look up propanes, and that is 103.8 kilojoules per mole. And if you try and look up oxygen, you will actually see that you can't find it. That is because that is its elemental state, and it is set to 0. Okay, so now we're going to plug this into a calculator. Make sure you do everything inside the square brackets first, and then combine the 2 different terms, and you should get an end result of negative 2043.9 kilojoules per mole. This tells us that the reaction is exothermic because it has a negative sign. Okay, and if on a test you were asked to do this, you'd be given a table of data so you could pull the information from. And we do have a worksheet that you'll be using that'll do that for you. Okay, so then over here, what is the enthalpy of reaction for the decomposition of baking soda? So I want you to pause the video and practice the calculation that we did in the previous one, where delta H is equal to the sum of the products minus the sum of the reactants using the coefficients. Okay, so determine the delta H of reaction using the heats of formation. So pause the video and do that now. We will do the next part together. So you should have looked up the data and seen that sodium carbonate, Na2CO3, has an enthalpy of negative 1130.7, and then you're going to combine that with the enthalpy of carbon dioxide and the enthalpy of water gas. And combining those terms, that's your products, and then you're going to subtract the 2 times the enthalpy of formation of the sodium bicarbonate or baking soda. When you combine those 2 terms, you should get a positive 135.6 kilojoules per mole, which should make sense a little bit. for a decomposition reaction because you're technically pulling apart the components of one molecule. So those should be endothermic. Not always, but that would make sense that it is endothermic and thus requiring some energy to make it happen. Okay, so now we want to see how much heat is involved if we use 7 grams of baking soda for your favorite cookie recipe. So we are going to convert 7 grams of baking soda, and remember that that is baking soda, to energy. So we know our energy conversion factor here. So I want you to pause the video and starting with 7 grams of the baking soda, I want you to use the balanced reaction in our energy we calculated and determine how much energy that requires. Please pause the video and do that now. Okay, so starting with your 7 grams, you should have used the molar mass to convert it to moles, then a mole ratio to convert it to moles of your reaction, and then you could use the energy conversion factor that we calculated in the previous part to determine the amount of energy, which should be 5.6 kilojoules total. Okay, so you're going to practice similar things. Make sure you have access to that appendix, and you're going to practice similar calculations in the You Do. Check your work, and thank you guys for tuning in.